Solubility in complex ions. Let's see, this is history. So I think I mentioned earlier that when we learned how to use ice tables to do equilibrium determinations, that you should master that and don't forget it, because we're going to come back to it again. We did in chapter 14 and 15, and again in 16, we're going to use ice tables. But now we're talking about solubility, and we're looking at actually two different types of solubility. One is that in which we've got an equilibrium set up between soluble parts of an ionic compound in aqueous solution and the precipitate. So there's an equilibrium established between those two. And these are going to be what we considered in the first semester to be insoluble compounds. In other words, they're only slightly soluble. But now we're going to learn how to determine what their solubility is exactly. So the term, the K value for solubility, we reserved KSP. So whenever you see KSP, that's a solubility product. Now, solubility is self-explanatory. What do we mean by product? Well, it has to do with the equilibrium that we've established here. I'm not going to draw that one on the board. Bismuth sulfide. So we have sulfur is a 2- bismuth 3+. So you get the subscripts there. And when we break it into ions in solution, we get 2 bismuths and 3 sulfides, but we don't get anything that can go in the denominator, right? Because the numerator, the denominator is from the reactant side, which is a solid, and the solids and pure liquids are never entered into equilibrium. So when we create the K for this expression, we only get the numerator, and that is multiply a product. That's why we call it a solubility product. All right. Now, this question refers to, let's see, what was the terminology we used in prior experiments? Equilibrium constant versus position. Okay, and the position for an equilibrium can be different depending on where you start. If you start off with reactants and products, you're going to end up with a certain equilibrium position. If you start off with only reactants, you may end up with a different position. But the constant, this K value, is always the same for a given temperature. Now we'll take that concept and discuss in terms of the solubility product versus the solubility. Okay. The product, of course, is always the same for a given temperature, but the solubility might be different depending on the temperature and other conditions, like common ions will have an effect, and we'll talk about that in a minute. These are not a one-to-one relationship, but they're similar in concept. So the point of that question is if you have a large solubility product, doesn't necessarily mean that you're going to have high solubility, because solubility products incorporate those coefficients as powers. So that could give you a huge product, but you still got a low solubility. Okay. Solubility is usually expressed in terms of moles of solute per unit volume. So solubility could be molarity. In other words, how many moles of the solid will be dissolved in a liter of solution. Or it could be grams per liter, right? How many grams of solid can be dissolved in a liter. Or sometimes, if you look it up in a reference manual, the solubility may be expressed as grams per 100 milliliters of whatever the solvent is, usually water. So you can get solubility in a number of different units of measure. This is a good practical approach. I think that's why the reference manuals will have it like this, because if you're trying to make up a solution, you want to know how much water to use and then how many grams of solute to use. It's just a simpler approach. Okay. And I already mentioned that one. The powers that are incorporated into the solubility product can inflate the value of K. So in order to compare solubilities, maybe I've got that on the next slide. Let me see. Okay. Here's one case in which you can compare solubilities of different solids based upon their K values. If the K value is the same structure, say you have calcium carbonate, right, would give you calcium and let's see, carbonate, like that. Yeah, that's right. And then sodium chloride would give you that. The K values for each one are going to be similarly constructed. So you would have this one times that one. And one for sodium chloride would be this one. And this one. So if they've got the same powers here and the same terms, then you can actually compare their K values and say which one is more soluble than the other one. Because when we calculate the solubilities, you find out that they're based upon the same K expression. So you're going to come out with the same solubility expression. Now, this one at the bottom is an example, but I think it's ahead of its time. I think we need to look at the ICE table first before we can understand why that one works. Now, of course, those are two different ones. So you can't directly compare the Ks for those two. So let's take silver chloride, use that as an example. And we'll build the ICE table. And if you're comfortable doing ICE tables for every one, that's fine. It just takes a little longer. If you can learn a pattern for extracting information, and the ICE table is sort of an intermediate, then there's a pattern that goes with solubility products. So this one where we have, and when we write solubility products, the solid always goes as the reactant. I mean, you can write it either way, but the solubility product is not the correct expression if you write it the opposite way. Okay. So the KSP for this one would be simply silver chloride with coefficients of 1 and 1. And this value, this is equal to 1.6 times 10 to the minus 10. So that's a very small value. And we can assume that it's only slightly soluble. Come on. There we go. All right, now how do we get that value? Well, if we set up the ice table, of course, this is not going to be part of the ice because it's a solid. So we would put initial change there and there. Initially, you have none. So we're going to add this much of each one, right? And it would, of course, come from this side, but that's not part of the expression. So we would have an X there and an X there, right? Or we could say, actually, if this is X, I think it would be more efficient to do it this way. Use S as solubility. There you go. So if we lose a certain amount here, then it shows up over here. Well, this is going to be S and this is going to be S. So this value, 1.6 times 10 to the minus 10, is actually S squared. So if we take the square root of that value, we get the solubility. And the square root is 1.3 times 10 minus 5. Solubility equals 1.3 times 10 to the minus 5. And since these values are in molarity, this value will also be in molarity. That's so many moles of silver chloride are in solution at this given temperature. And we have to assume that this is a standard temperature, 25 degrees Celsius. So if we go back, there's Courtney. We've already started the lecture, Courtney. We're not too far into it, though. If we go back to that previous slide, we see there's sodium chloride, which would be 1 sodium and 1 chloride. So you're going to have the same S squared. Sodium chloride gives you the same expression here. It's just a different value for the K. Okay. For sodium phosphate, let's see. I should erase that. Sodium phosphate is going to be a little bit different because we have 3 sodiums and 1 phosphate. So we have 3 sodiums and 1 phosphate. Well, it should be 0 anyway. This is 0, 0, 0. And if we lose one of these, what's going to show up over here? Well, 3 are going to show up over here, right? Because for every one of these, you get 3 of those. Right? But for every one of these, you only get 1 of these. So we have 3S and S there. So S still represents the solubility of the compound. But the number of ions, the concentration of ions going into solution are these 2 expressions. Then if we set up the KSP expression, we find that the solubility product should be sodium to the 3rd power and phosphate to the 1st power. So what's sodium? Sodium is 3S cubed. and then S for the phosphate. So 3 cubed is what? 3 times 3 is 9, 27, right? So 27 S cubed times S is 27 S to the 4th. That's where that came from. Okay. It's kind of like doing double dipping. You're going to get the 3 here for the power, but you're also going to get the 3 here for the stoichiometry. So it might be useful to just continue to use ice tables. They'll keep you out of trouble. Okay, so we did that slide already. Silver phosphate. Calculate the solubility of silver phosphate in water. All right, let's do that. So our equation is going to be silver phosphate, which we know is insoluble. This is a 3-, so we need 3 of these. Set that up as 3 silvers and 1 phosphate. And you see similarities here between this one and sodium. So what we should get is, let's see, 1.8 times 10 to the minus 18 equals the KSP. And that should be equal to silver cubed and phosphate to the 1st power. And then if we say this is, we're going to lose a certain solubility there, and this is 0, 0. And let's see, change in equilibrium. Then we're going to get 3 S here and only 1 S there. So 3S, S, and here we get again what we have. We end up with 27 S to the 4th, just like before. Okay. So what do? Well, we take that and divide it by 27. Okay. And then we take the 4th root of it to get S. Did I go too fast? Okay. So let's see. 1.8 exponent minus 18 divided by 27. And then my calculator doesn't have keys for roots like that. I have to do powers. And the 4th root is the same. The 4th root of X is the same as X to the 1/4 power. Okay. So that's the way I have to do mine. I have to do 0.25 and then do my exponent. So we should get S equal to 1.6 times 10 to the minus 5 molar. Okay. Some calculators have a root key, but mine doesn't. All right. How does the solubility of silver chloride in water compare to that of silver chloride in acidic solution? Made by adding nitric acid to the solution. All right. We did talk about common ion effect already, didn't we? How it affects the solubility? No, maybe not. Okay. For instance, using this as our expression, say we set up an equilibrium in aqueous solution with silver phosphate and its ions. Well, actually, we didn't set up an equilibrium yet. We have a solution with some silver already in it. Okay. Then we put some silver phosphate in the solution and wonder what's the solubility of that added silver phosphate. So we could add silver as silver nitrate. completely soluble. Okay, so we've got some silver in there already. That would change this value to some whatever, some value there. That would change the expression here because now you'd have this plus 3s. And that would go into your expression over here. That's the quantitative approach. The qualitative approach says if you've already got some of this in there, you're not going to dissolve as much of this, according to Le Chatelier. Okay. So if we look at this possibility here, silver chloride is only slightly soluble in water. What if we create an acidic solution? Right? So we've got two reactions there. We've got nitric acid that completely dissociates. Actually, that equilibrium arrows for nitric acid are irrelevant because nitric acid is completely soluble. So it would produce all hydrogens and nitrates. Okay. So if we combine those two equations, we get silver chloride and nitric acid yields silver, chloride, H, and nitrate. Does that have an impact on the solubility? Well, look at the other side of the equation. Do you get any reactions that give you a pure compound or like water or another solids? Well, silver plus hydrogen, silver plus nitrate, no, that's completely soluble. Hydrogen plus chloride, that's completely soluble. So this has no impact on the solubility at all. It's an acidic solution, but it doesn't affect the solubility because there are no common ions that will react and remove any part of the dissolved solid from that picture. Okay. There are no common ions. Now, I think on the next slide, we're going to introduce a common ion. Solubility of silver phosphate, okay, in water compared to that of silver phosphate in acidic solution. Now, in this case, you add nitric acid. What do you get? Well, we know that phosphate ion is derived from a weak acid, which means it's a very strong base. It wants protons. So when you add protons to that solution, it removes phosphate. And if you remove phosphate by adding acid, right, take that out of the picture, you're going to draw more of this. Le Chatelier says you're going that way. You're going to make it more soluble. Okay. Because the phosphate is a strong base. And in fact, hydrogen phosphate is a strong base also. And dihydrogen phosphate is a strong base. So you're going to end up with phosphoric acid, which is only slightly soluble. It's a very weak acid. So you're going to go through actually 2 proton extractions and take most of that out of solution. So you might be able to completely solubilize, depending on how much silver phosphate you put in solution as a solid. You might be, with enough acid, you might be able to completely solubilize silver phosphate just by adding nitric acid. Okay, that's one way to make a slightly soluble compound completely soluble. Later on, we're going to look at a second way. There are 2 ways. And one way we just approached is to attack the anion and remove it. Right. The other way we're going to get to when we talk about complex ions, we're going to remove the cation. So there are 2 ways to solubilize. If you cannot, for whatever reason, if you cannot remove the anion and solubilize the solid, then you have to go to the cation. And when we do that, now we're talking about next week's lab. Okay, how does the KSP of silver phosphate in water compare to that of silver phosphate in an acidic solution made by adding nitric acid? The KSP is a constant. The only thing that'll change it is temperature. Right? So the KSP is the same no matter what, whether you have common ions or not. We just want to make that point. You may be tempted to say, "Ooh, more soluble? KSP must be larger." Nope. KSP is a constant. The only thing we've changed is, let's see, is the solubility. Okay, calculate the solubility of silver chloride if you have a starting solution of 100 milliliters of 4 times 10 to the minus third molar calcium chloride. Since chloride is a common ion, it should have an impact on the solubility. Okay, so let's make room and change our equation. Let's just erase all this. So now we're back to silver chloride. Solid chloride. Aqueous. Okay. The KSP for this is 1.6 times 10 to the minus 10, is it? Yeah. And the expression is still silver and chloride. Okay. Now, what are the conditions? Well, we've got calcium chloride, which is completely soluble in water. And it's a 4 times 10 to the minus third molar. Okay. So we have, let's put that over here. 4 times 10 to the minus third molar calcium chloride. Okay. So what concentration of chloride are we putting into solution? Because calcium is not going to affect this, because calcium reacting with chloride is just going to produce the same thing as we put into solution. So we're really interested in the chloride. That means 8 times 10 to the minus third chloride, because there are 2 for each one. Okay. So now, let's see. Well, there's our ice table. We're going to calculate the solubility. So we're going to have an ice table. And initially, we have 0 there. And we're going to lose. That represents the solubility of silver chloride under these conditions. And that means we're going to add some here and add some here. Oh, mistake. 8 times 10 to the minus third molar. Okay, so now we're going to have that much silver, and we're going to have 8 times 10 to the minus third plus S there. Okay, so this expression is going to be S here. This is going to be 8 times 10 to the minus third plus S. Okay. So we factor through there. Now, is the solubility going to be, what was the solubility before? Silver chloride. We did that one, didn't we? Let's go back. Silver chloride. That's silver phosphate. Silver chloride, there it is. 1.3 times 10 to the minus fifth. Right? And we know it's going to be less than that because of the common ion. So can we drop S out of this equation? Well, 10 to the minus fifth, even if it were pure aqueous solution, that's 2 orders of magnitude difference. Right? It's going to be a whole lot less. So I think we can estimate and say that's S times 8 times 10 to the minus 3. That way we don't get a squared value in there and have to do a quadratic. Okay. So this is equal to 1.6 times 10 to the minus 10. That means S should be equal to 1.6 times 10 to the minus 10 divided by 8 times 10 to the minus 3. Correct? Yeah. Okay. I could probably do that in my head, but I don't want to right now. Too risky. Okay, I get 2 times 10 to the minus 8 molar. Okay. And that's 3 orders of magnitude less than the solubility in pure water. Right. So I think we're safe. I mean, we could do the 5%, but in the interest of time, let's see. Here we go. There we go. Yep. That's the way we approached it. 100 milliliters doesn't matter. That's superfluous. I mean, we could get more silver chloride in solution with a larger volume, but it doesn't change the solubility because solubility is an intensive property. And the amount that goes into solution, of course, is an extensive property. We just need more volume to get more in solution, but it doesn't change the concentration at all. Okay, so we can see from this calculation that solubility, because of that common ion, the chloride, solubility is decreased. We're putting pressure on this solubility in that direction. There's less silver chloride going into solution that way. What if we use calcium nitrate? Now we don't have a common ion. So the solubility is going to be the same as before, 1.3 times 10 to the minus 5. So we look for the common ions, things that can fit into this equation and influence the solubility. Okay. We can erase this. I'll leave that up there for now, except for this. Take that out. And we just leave the equation so we can talk about it. So when you mix 2 solutions of one has cations in it, one has anions in it, it's interesting to ask the question, will a solid precipitate? So we're going back the other direction now. Instead of solubilizing the solid, we're saying if we mix a solution that has silver ions in it and chlorides in the ions in the other solution, put them together, are we going to get a precipitate? Well, the answer to that question is to calculate the Q and compare that to the KSP. If the Q is greater than the KSP, you will get a precipitate. If the Q is less than the KSP, then you won't get a precipitate. What does that mean? Well, if these concentrations are high enough, then they're going to drive the reaction back that way. Le Chatelier says they are. If they're too low, then they're not going to go this direction, and there's no solid in there anyhow. So you're going to have these in solution, they're going to stay in solution. There we go. So here again, we use that convention, parentheses rather than square brackets. Parentheses references Q's, square brackets are equilibrium. Now, the practical benefit of this method is to selectively precipitate cations from solution. If we know we've got a solution with, say, barium and silver in there, right, and we've determined that qualitatively by some other method, then how can we separate those two ions? Well, if we add hydrochloric acid, we form the silver chloride precipitate. All we have to do is be sure there's enough chloride in there for the Q to exceed the K, and we will precipitate silver chloride. And barium, though, barium chloride is completely soluble. Let's see. Yeah, leaves barium behind. Now, we used hydrochloric acid because we don't want to contaminate the solution, what's left over. If we're gonna isolate silver from barium, we don't want to put sodium in there. I mean, we'd still precipitate the silver chloride, right? But now we've got barium and sodium together. So we kind of shoot ourselves in the foot if we do it that way. Okay, suppose we have a more complex mixture. We have copper 2+, mercury 2+, nickel, and manganese both 2+. And we know that the sulfides of these cations are insoluble. I mean, based upon our first semester chart. But how are we going to separate copper and mercury from nickel and manganese using sulfide? We're focusing on the sulfide ion. Well, we look at the K values, right? If we add a very small amount, or we create the conditions where you have a very small amount of sulfide in solution, then you're going to precipitate the cations, cation sulfides that have the lower K value, the lower solubility. Let me put it that way. That's proper to say lower solubility. So we need to arrange the conditions so that the sulfide concentration is low. Then the very insoluble mercury 2 sulfide and copper 2 sulfide will precipitate and leave the nickel and manganese behind. How do you do that? Well, we look at the equilibrium expression for hydrogen sulfide and for hydrogen sulfide. Overall, it's 1.2 times 10 to the minus 20. Well, how do you keep very small amounts of sulfide in solution? You arrange your situation so that you have acid in solution, hydrogen ions. If you have hydrogen ions, they're going to combine with the sulfide ions and take them out of the picture. So in acidic solution, hydrogen sulfide is going to produce very small amounts of sulfide, which favors the precipitation of only copper and mercury. So that's how you get the copper and mercury out. Then to go after the nickel and manganese, you want to increase the sulfide concentration. And that's where we add base. We add hydroxide ions. Now, how do you get them in there is a question, because right, if you use most hydroxides that are soluble, you're going to contaminate your solution. But we get the copper and mercury out first with an acidic solution of hydrogen sulfide, and then we add hydroxyls, which do what? The hydroxyls combine with the hydrogens to make water, and that drives the reaction to the right, produces more sulfide. Now we can take out the nickel and the manganese. Question is, how do you get the hydroxide in there? Well, actually, that's not a problem. It just occurred to me. If you add sodium hydroxide to that solution, sodium is not going to precipitate, right? Only the manganese and the nickel will precipitate, so you're not contaminating them. Okay, I just, you know, I could have had a V8. Okay. So this is an abbreviated version of selective precipitation of cations. Right? If we know that we only have those four in there, that's the way we would separate them. But we've got a bigger picture to deal with, right? Suppose you have a very complex mixture of cations, like at the top. And we've got them separated into color-coded groups so that we're removing the purple first, and then the yellow, and then the orange, and then the green, and then the purple again. And we do those in steps. So the first step, we can get silver, lead, and mercury 1, right? Hg2 with a 2+ charge means that's a mercury 1+. We can get those three simply by adding hydrochloric acid. Those will make the insoluble chlorides. Now, once they're precipitated, how do you get them out of there? You just filter them, right? Filter the solids out, right? And then take the solution and do the next thing to them. And the chlorides are going to be caught on your filter, and you can remove those, dry them, do whatever you want to with them. Now, at this point, you've got silver, lead, and mercury together, but at least you don't have all those other contaminants. You'd have to go through another step to separate the silver, mercury, and lead from each other. But that's another problem, it's too complex for this course. If you take a course in chemistry quantitative analysis, then you'll learn how to separate those. If you need to separate them. If you don't need to separate them, you just need to quantify how much they're of each one. There are several methods you can do. In fact, if you only need to know how much of each one is in there, you don't even have to separate them. All right. You just make sure they're all in solution. You run them through what I used to use was an inductively coupled argon plasma spectrometer, which is a mouthful, but it would quantify all of those cations in just one shot. In fact, it takes more time to calibrate the instrument than it does to run the sample. Okay, once you've got those out, now you've got an acidified solution. Well, but it's acidified. If you add hydrogen sulfide to it, that acidic solution means that you're going to have a very low concentration of sulfide, right? So now you can remove the second group, which are insoluble sulfides, but they have a very, very low K value. So you can get copper, bismuth, cadmium, lead 2+, excuse me, Well, actually, we're taking out lead there, aren't we? Lead chloride. Okay. So that's not bad. You're scavenging lead in 2 steps, but you can get all of those cations with low sulfide concentration. Then we want to increase the sulfide concentration. We just add sodium hydroxide and increase the pH into the 7 to 8 range. Now you can get the sulfides that are more soluble. And you can also get not just the sulfides, you can get the hydroxides that are insoluble. Aluminum hydroxide, iron 3+ hydroxide, and chromium 3 hydroxide, along with the sulfides. So you still got a complex mixture in there. And then what do? Well, now what do you got left? Well, we've got barium, calcium, and magnesium left. So we know that the carbonates of barium, calcium, and magnesium are insoluble. So we add sodium carbonate, right? We've already added sodium as sodium hydroxide, so sodium carbonate, a little more sodium won't matter. But now we got carbonate in solution, and it will precipitate the barium, calcium, and magnesium. So what's left? Well, if you have any of the alkali metals, sodium, potassium are the only ones given there, but you could have lithium, rubidium, cesium. Any of the alkali metals are always soluble. So that's what's left in solution along with the ammonium in our scenario here. Now, how do you get those out? Well, the alkali metals are easy. You just dry the solution, evaporate. But the problem there is that ammonia, we're still in basic solution. So we've got ammonium and hydroxyl. With all that base in there, you're driving this reaction back to ammonia. Ammonia is very volatile. So if you try to dry that solution, you can still get the alkali metals, but you're going to lose all the ammonium. So what do you do then? Well, you could distill it, fractional distillation. You could boil the solution, and the alkali metals are not going to evaporate, and the ammonia and water are going to come off, but they have 2 different boiling points. So the ammonia is going to come off first, and you probably would have to have a pretty cold condenser to get the ammonia, but it can be done. Now, I'm sure there are better ways to do it than that. It's the only one that comes to mind at the moment. There you have selective cation precipitation as a method of separating cations using their solubilities. Okay. Now we're going to look at, oops, let me put that back up there. We're going to look at solubilizing slightly soluble solids, not by attacking the anion. In this case, we can't, right? We can't acidify this solution. It won't have any impact on the solubility. So in this case, when we have silver chloride, we're going to have to solubilize that by attacking the cation. And that's where complex ions come in. Complex ions are stable, soluble forms of the cations. And in order to do that, you need some type of what we call a ligand. Think of a leg, something, this is the cation and that's my leg, and it's holding me up. In the case of silver, if we want to use ammonia, We need two ammonias. We need two legs, right? So if we add ammonia to this solution and we have two of them, then what we get is silver and ammonia. And still got the plus charge. And this is completely soluble in water, but the equilibrium favors that direction. Well, actually, the equilibrium is back this way, but we put so much ammonia in there that it drives the reaction this way. And when we do that, we have a coupled reaction, like our Le Chatelier. We couple this reaction, it removes silver and solubilizes the silver chloride. Okay, now this is an equilibrium situation. So there's an equilibrium constant for this reaction right here. And it's called, actually for this one is a KSP. This one is a KF, formation constant. What's the constant referenced here for the formation of the complex ion? And I gave you a handout how to name these complex ions. They also call coordination complexes. I'm not going to test you on that. That's just information. And if you ever need to name one of these compounds, there you go. So this would be silver 1 diamine. Okay. Let's see. All right. Now, when this is the overall reaction, what actually happens is for each one of these silvers, it's like polyprotic acids. For each one of these silvers, we're going to add an ammonia and set up an equilibrium here. Right? And then we're going to take this one, add another ammonia. And that gives us our final product. And these are all aqueous. Aqueous. Okay. So the overall formation constant here is the combination of those two. A different example. In this case, beryllium forms a complex with 4 fluorines. The fluorines are the ligands. You'll notice that in this case, the first reaction is highly favored to the product. Second reaction is also product. Third product, fourth product. Less and less, but overall, the K value is 10 to the 12th. So you get the formation constant highly favored. And each step, I mean, once you form the BEF plus, then it's ready to go for the next one. And it's got 1,000 times order of magnitude, a little less, but it still goes to the right, to the right, to the right. So it makes sense that the K value formation constant is 10 to the 12th in this case. Okay. This slide emphasizes the 2 ways that you can solubilize an insoluble compound. If the anion is a good base, right? It's derived from a weak acid. If it's a good base, you can acidify it, and that will draw it in solution. That's attacking the anion. The second one is if since the chloride is not a good base, it's from a strong acid. hydrochloric acid, then you can't attack it with the acid. You have to go for the cation. So those are the two possibilities for two strategies for solubilizing these slightly soluble ionic compounds.
First, let's calculate the molar solubility.
Okay, hold on. Back up. All right. Let's see.
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we get in part A to the solubility that we're going to get in part B. And in part B, it's no longer pure water. We're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water, and some of the silver chloride is going to dissolve, but most of it's going to stay in the solid form. So silver chloride is only a slightly soluble compound. So there's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver +1 cations in solution, and there are also chloride anions in solution, and we have our solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ice table. So our initial concentrations, our change, and finally our equilibrium concentrations. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product are 0, right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride, and we're going to call that X. So we're losing a certain concentration of our silver chloride. If we look at our mole ratios, for every 1 mole of silver chloride that dissolves, we get 1 mole of silver +1 cations in solution. So if we're losing X over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1:1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anions. So over here we get a +X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of Ag plus raised to the power of the coefficient, so raised to the first power, times the concentration of chloride anions, Cl minus, raised to the power of the coefficient to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the -10. So we put in here 1.8 times 10 to the -10. And this is equal to, this would be X times X. So this is equal to X squared. So we can get out the calculator and solve for X. So we have the square root of 1.8 times 10 to the -10. So we take the square root of that, and X is equal to 1.3 times 10 to the -5 if we round that. So X is equal to 1.3 times 10 to the -5 molar. So that's the concentration of, let's say, our silver +1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So it's a very small molar solubility. So silver chloride is only a slightly soluble compound. Let's see what happens when we have ammonia present instead of pure water. So we have a 3 molar, right? We have some ammonia present now. What happens when ammonia is around silver cations? Right? We get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. And let's show what's happening. So if we have a silver +1 cation, right, we have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw one in on that side. I'll draw another one in on this side. Remember your definitions for Lewis acid, Lewis base, right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver +1 cation. Right, so ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver +1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. This is a very high value for the equilibrium constant, right? So the equilibrium lies to the right, and this is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to pick up that silver ion and essentially remove the silver ions from solution. So if we go back up here and think about our equilibrium, right, if we have ammonia present, we're going to be removing silver cations from solution. Right, so we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present, because of the formation of our complex ion. So if we added some ammonia, right, if we added a solution of ammonia here, we could get our silver chloride to dissolve, right, because it's more soluble because of the formation of a complex ion. So let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion, which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound, silver chloride. And next, we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at two reactions. We've looked at the solubility equilibrium for our slightly soluble compound, and we've also looked at the formation of our complex ion. Now let's add those two reactions together to get our net reaction for what's happening, right? So we're going to add our two reactions together to get a net reaction for what happens when you put silver chloride in ammonia. Right, we have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. So we have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction, and if we added those two reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add two reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those two reactions. So K is equal to KSP times KF. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7th, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative 3rd. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. So we set up our ICE table, so our initial concentrations, our change, and then our equilibrium concentrations. And let's pretend like we're starting out with our solution of ammonia and we haven't added any silver chloride yet. So let's go back up here and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia, so let me put that down here. So our initial concentration for ammonia is 3 molar. And if we haven't added any of our silver chloride, then we don't have any of our complex ions. So the initial concentration of our complex ion is 0, and we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve, and so we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia. So we write minus 2x here. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing X over here, we'd be gaining X over here for the concentration of our complex ion. And same thing for the chloride anion, because our coefficient is a 1. So we're going to gain X for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x, our concentration of complex ion is X, and our concentration of chloride anion is also X. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here, so concentration of our complex ion, and we raise the concentration to the power of the coefficient, so to the first power. This is times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the first power. We also have some reactants here, so we leave silver chloride out because that's a solid, right? But we have ammonia, so this is all over the concentration of our reactant, so this is over the concentration of ammonia. And notice our coefficient is a 2, so we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is X, and our equilibrium concentration of chloride anion is X. So on the right side, we would have X to the first power times X to the, let me take that out, times X to the first power. Right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant K, which is 2.9 times 10 to the negative third. So 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. So let me write this out. We would have x squared over 3 minus 2x squared is equal to 2.9 times 10 to the negative third. And so what we could do here, these are both x squared, right? These are both x squared, so we could just say that this is all squared on the right side. And then we could take the square root of both sides, right? So take the square root of 2.9 times 10 to the negative third, and take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative third is equal to, let's round that to 0.054. So it just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3, and if you round that, you're going to get about 0.16, and 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 is equal to, we put both x's on one side, this is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. And so now we need to solve for x. Right? So we've done our math here. So we have 0.16. We need to divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration, right? So this is our molar solubility. If we go back up here, x equal to 0.14 molar, Right, so that's our concentration of complex ion in solution at equilibrium. That's our molar solubility of silver chloride. Right, so it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right, so in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We've increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
When we talk about the lab, we're actually going to go backwards. We're going to calculate the formation constant for the silver 1-diamine complex ion. And we have something to compare it with there. Okay. All right, so I think a lot of this compared to what we've just saw on that screen is going to be repetitive. The relevant species here, silver chloride and ammonia, are derived from these reactions and then form the complex ions. All right, we have those values for each of those steps. Then if we the equilibrium lies far to the right, we know, because for the formation of the complex ion lies far to the right. It's going to solubilize silver chloride. So when we combine the three, we get this value, which is close to what Saul Kahn was showing us on his video. And since the equilibrium for this overall equation lies to the left, we can see 10 to the minus 3. That's why ammonia has to be such a high concentration, so that it drives the reaction to the right. I'm not sure what we're using in the lab. 3, 5, 1 molar. So we're going to use 1 molar instead of 3 molar. And it involves a titration. A different kind of titration. Not acid-base this time. This is a solubility titration. Okay. Actually at the back of that hard copy of your procedure, I give you an explanation, which is not something you need to memorize or understand, but I give you an explanation for why we can put ammonia in solution, and it makes a basic solution because ammonia does react with water, slightly react with water, and produce hydroxides, but it's over 99% is as ammonia. Reason it needs to be that way is because the ammonium ion does not form the complex ion. Only the ammonia does. And the reason it does, Saul Kahn showed you there, was because ammonia has those 2 electrons available. And that makes it a Lewis base. I had to think for a second. A Lewis base, I think. Is that right? Let's see. Electron pair versus hydrogen. So this is a donor. This is an acceptor. Yeah, Lewis base. So the ammonia is a Lewis base. Was it donates electrons, and the ammonium can't donate electrons because they're tied up with another hydrogen. So we have to have ammonia in solution, and that explanation shows you that we're well over 99% ammonia in that 1 molar solution. In this case, we have 10 molar. So if we run through those same calculations as before, then we end up with a much higher solubility than 0.14 that were shown on the previous video. Okay, come on, 0.47, 4 times the solubility. But you have to go from 3 molar to 10 molar ammonia to do that. Now, how much is left over? Well, we find out, we just enter the equilibrium expression for ammonia, which is 10 minus 2x. We just plug in the x and we find that there's still 9 molar ammonia still in solution. So if you hold it up to your nose, right, it's smelling salts. It's going to knock you down. I think this is the last slide, isn't it? Yeah.